Hello, welcome to this video. Today we're going to talk about this problem. So let's let P be a polynomial with whole number coefficients. So something like negative x squared plus 2 is valid, but x plus 0.5 is not valid. 0.5 is not a whole number. And let a0 be some whole number. And define the series an as follows. So an plus 1 will be p of an. So we're going to start with a0, then a1 is p of a0, a2 is p of a1, a3 is p of a2, and so on and so forth. We're basically repeatedly applying our polynomial p. And we also know that there exists an m bigger than or equal to 1 such that am is equal to a0. Show that the smallest number satisfying this property is 1 or 2. Or in other words, show a0 is equal to a1, or maybe if a0 is not equal to a1, it's equal to a2. So let's begin. So for the first thing, when you see whole number p is a polynomial with whole number coefficients, first thing you should be thinking about, for every whole numbers a and b, a minus b divides p of a minus p of b. And this is usually useful in questions with polynomials with whole number coefficients. If you're curious about why that's true, I'll actually leave it to you to prove it. It's not that difficult. But here it seems that it'll be useful to us as or also the entire essence or the way we build our series an is by applying p. So it seems like this property should really help with the problem. So let's try it. Let's see maybe what is an plus 1 minus an. Well, an plus 1 is p of an, and an is p of an minus 1. But notice that we know by this property that an minus 1 divides into this. And I should mention also and an minus 1 have to be whole numbers because you can basically sort of show with induction. a0 is a whole number, and if you put a whole number inside a polynomial with whole number coefficients, you'll obviously still get a whole number. And so a1 would be a whole number, and then a2 would be a whole number, and so on. So every term in the series is a whole number. So we can use this, and we get an minus 1 divides into an plus 1 minus an. Now, this seems like a very important fact, so let's maybe label this as bn minus 1, and this as bn. So b0 is a1 minus a0, b1 is a2 minus a1, b3 is a4 minus a3, and so on. And now we know in our series that each term divides into the next term. But now we know that at some point the series an repeats itself, because a0 will turn into an. So from that point, let's try to look at bm. It seems like an interesting number. bm is am plus 1 minus am, but am plus 1 is exactly, by definition, p of am, and this is minus am. But notice, am is exactly equal to a0, so this is p of a0 minus a0. But p of a0 minus a0, this is p of a0 is exactly a1, so this is a1 minus a0. But by how we defined the series b, this is precisely b0. So bm is equal to b0. But from this property, we can understand something very interesting. b0 divides into b1, which divides into b2, which divides into b3, and so on, until this we have something dividing into b minus 1, which divides into bm. But bm is b0. So if a number divides into a number, so if a number is divisible by a number and divides into that number, it has to be plus or minus the number. Because remember, we're not talking about natural numbers here, we're talking about whole numbers. So for example, -2 divides into 2 and is divisible by 2. And obviously 2 as well, but these are the only ones. So now we know for all I smaller than or equal than m minus 1, not a, but bi is equal to plus minus b0, or in other words, the absolute value of bi is equal to the absolute value of b0. But now from this, we obviously get absolute value of b0 is absolute value of b1, and so on until it's the absolute value of bn minus 1. Okay. Now, here, it seems like we've, this is obviously very important, but we need to get back to the series an. So, we need to somehow get rid of the absolute value. And the way we'll do that is by looking at two different cases. One, there is either there exists n such that bn is equal to negative bn plus 1. Of course, n needs to be in the appropriate range from 0 to n minus 2. Or, for all n in the appropriate range, bn is equal to bn plus 1. These are obviously the only two cases we have. So, let's look at this case first. If we have some n such that bn is equal to negative bn plus 1, let's just use our definition of bn. We now know an plus 1 minus an is equal to negative an plus 2 minus an plus 1. Or in other words, an plus 1 minus an plus 2. Notice, an plus 1 cancels out, and we'll get an is equal to an plus 2. What does this tell us? Well, let's now, because these numbers are equal, obviously p of them will also be the same. So, so let's do this. We'll apply p to both sides. P of an is exactly an plus 1. P of an plus 2 is exactly an plus 3. And if we keep applying p's, we'll get an plus 2 is equal to an plus 4, an plus 3 is an plus 6, and so on. So basically, we always keep that difference of 2, and we'll be able to keep it going up until am is equal to am plus 2. Now, am is equal to a0. Am plus 2 is p of am, right? So this is basically p of am plus 1, and am plus 1 is p of m, so this is p of am. But am is a0, so this is p of a0, but p of a0 is a2. So we get a0 is equal to a2. Meaning that either a0 is not equal to a1, and then the smallest number satisfying our property is 2, or a0 just so happens to equal a1, and then the smallest number satisfying this property is 1. So in this case, we saw that we indeed proved what we set out to do. So this case is done. Now let's do this case. Okay? Now let's deal with this case. For all n, bn is equal to bn plus 1. Let's again use So basically, this means b0 is equal to b1, b1 is equal to b2, b2 is equal to b3, all the way on to bm minus 1. So let's mark this symbol with, say, d. If this is some number d, well then we know an plus 1 minus an is equal to d, or in other words, an plus 1 is equal to an plus d. This is exactly an arithmetic sequence. We start with the number a0, and we keep adding to it the same number, d, to get to the next number. So a1 is a0 plus d, a2 is a1 plus 2d, and so on. And in general, in an arithmetic sequence, an is equal to a0 plus n times d. But now, am suddenly seems to really help us out here, because am is equal to a0. But this is also, by our arithmetic sequence, a0 plus n times d. So a0 cancels out, n times d is equal to 0, m is bigger than or equal to 1, so we can divide by it, d is equal to 0. But if d is equal to 0, an is just always equal to a0. But then it's just for specifically 1, a0 is equal to a1, and we get the smallest number satisfying this property has to be 1. So in this case we got 1 or 2, in this case we got 1. So in general, the smallest number satisfying this is 1 or 2. And now just for the finishing touches, let's also show 1 can be the smallest number and 2 can be the smallest number. So for 1, let's pick p of x to be just x, because then p of a0, which is a1, would be a0, which works. Which tells us, yes, that the smallest number satisfying this is 1. But for 2, first of all, let's say a0 is not 0. Let's pick like a0 is equal to 1. And then p of x would be negative x. So we would go a0, negative a0, a0, negative a0, and so on. And then we would get a1 is not a0, but a2 is a0. So the smallest number satisfying this could be 2. It's not that we missed something and it's actually always 1. And we showed that it has to be, that can only be 1 or 2. Cannot be like, smallest number cannot be 3. So finally, that's it. If you want more content like this, please subscribe to my channel. I'll be uploading more interesting problems and things like this in the future. And finally, that's it.